Okay, so today we have Jordi Pinheiro. He's come from the complex system lab in Barcelona, and he's a physicist by his original training. But he's moved on to work on complex system, and in particular, he's have his interest on the information theory for living system. And also, he have been working on like ecosystem neural network applied to living system and problem related to stochastic thermodynamics. So just go ahead.
Well, thank you, Juan, for your nice introduction, and thanks all the organization also for inviting me here today to talk about this work. I want to start by saying that this work is still not on archive. It will be very soon, and I apologize for that. But if you guys want to see the exact calculations that I do and so on, please just ask me, and I will either send it to you or we can discuss it at the end, right? And I don't know if you see here, but this work is centered in trying to understand information bounds or information limits on production of replicator systems. These are minimal chemical systems, all right? This is going to be the outline of the talk. So I'm going to give you, first off, a little bit of a broader context. Where do I, yes? Oh, by the way, please interrupt me anytime.
That's okay there.
Here, like this? Yeah. Oh, yeah, much better. Great. So this is going to be the outline. I will give you some context, right? I'm also going to be specifying what are the research goals for this project. And I'm going to go into a little bit of a detour. I'm going to talk about gambling a little bit. It's going to be fun, hopefully. Then I'm going to go to our general setup for how we build this system. This is how we build our model, and then going into our main results. Finally, I'll give you an example, which is actually kind of a very driving aspect of this project, how to actually push this into the actual realistic realm, right? And go beyond the theory. So I'm going to talk about that for a while, and then we're going to wrap up. And please, again, I just said it, but for all the people, interrupt me at any point. I'm happy to take questions during and after, etc. So let's start with a bit of context, right? Where do we place ourselves here? What are we thinking about? So we're thinking about the context of living systems, and we want to be thinking in terms of information theory. But you know, you might have heard of this. Like, information theory is this theory that was built up in the 50s, right? And from then it has like a huge success, specifically in engineering. And it's opened so many venues of research and actual applications. And more people are trying to understand how this sort of approach, where you actually can understand correlations between, originally it was an emitter and a receptor, but here in living system, when we think about living system, we think about an environment that might be fluctuating, in some kind of system, for example, an organism. But understanding these correlations might not be the important aspect when you're thinking about biology. Sometimes you are correlated with something, but really there's not necessarily something useful out of this correlation. And this could very much happen in living systems. And so Artemy Kloczynski and David Wolper, Artemy is a close collaborator on part of this project. They came up with this kind of like a different approach to try to understand information from a semantics perspective. And the word semantics here just means this distinction between relevant and irrelevant information and trying to stress out the relevant part. And the context was, again, trying to understand this in living systems. Okay, this is just broad aspects. And essentially, one important thing that they did, and I'm not going to go into it, but just for you to maybe capture the imagination of what they did, was think about a phase space, and then think about how can you decorrelate manually, think about all possible decorrelations you can do from your system and your environment, and see how these kind of perturb the kind of trajectories that you will see. But then on top of it, you add something else. There's not just like correlations and that's it. You have something called a viability function, right? And this is actually, this is probably one of the biggest problems with this framework, is that it's intrinsic to each case that you want to study. And the question here was like, okay, how much information really will affect viability function? How much information will not? And the information that will not affect viability function, this is called irrelevant information. And so this is the kind of setup that we start with. But also let me mention that in this context of understanding the value of information in living systems, is also very important and impactful prior work from people like Lachman and Bergstrom, where they started asking this question in the context of evolution, right? Imagine that you have different phenotypes, and you can, for example, change your genes so that you move from one phenotype to the other. And in facing kind of a fluctuating or a random environment, you might be more fit in certain way or not. And then if you think about it, you can kind of establish and already using this work, you can kind of establish better strategies, you know, given a random environment. So this was the kind of ideas that were explored here. Also over here, while this is a very famous paper, by the way, I don't know if you're familiar, but Castle and Leiber kind of established a similar idea, but on the context of phenotypic switching in bacterial ecosystems, right? And so here they were looking at growth, like actual total growth over time. And they got very nice, interesting results that started connecting ideas of information to this evolutionary, if you want, adaptive system. So far, so good, right? I just want to mention very briefly that, in a sense, this is not a paper about Bernstrom that's on arXiv at the moment. And it's kind of a generalization of what I wanted to highlight here, because a lot of this, surprisingly, was already kind of hinted at by Kimura. Even though in a very kind of early stage way, he was already thinking about very, very simple genetic population problems where you have two alleles and one outcompetes the other. And he found out that there was this kind of information theoretical contribution, and he called it substitutional law. We're going to see an example where this applies next, but I just wanted to highlight this very unknown paper of him, and I think it's one of these nice little nuggets of gold that you can find in the literature. Again, we're thinking about, okay, how can we apply information theory in biological systems, right? And so this is our background. And I want to state what is the research goals for this specific project with all of this kind of thinking about this from our back of our heads, right? So first off, we want to have a slightly different context than the ones that I just stated, because we really want to have like something finite, something actually realistic, something that I can build in the lab. I'm not just thinking about, you know, species that are in a kind of an abstract way existing somewhere, right? And I look at phenotypic switching and so on. I want to have something that I can account for mass conservation. I can have something more physical. And of course, chemistry is kind of like the go-to place to do that. So by that, I mean, I want to use kind of finite or bounded systems that are going to be my realm of application. And in particular, and this is kind of the first thing that you can start to study, I'm going to focus on autocatalytic self-replicating molecules. And I'm going to be talking about this for a while, right? If you don't know what these are very simple reactions that you basically use some substrate and they use it to replicate themselves. And this exists in the lab. And importantly, there's going to be no adaptive mechanisms in the sense that there's not going to be any genes that can mutate or anything and you can adapt this way. There's nothing like that. It's very simple, very run-of-the-mill chemicals that, okay, maybe they are not so run-of-the-mill because some of them have been only synthesized a year ago. But the point is that they don't involve complex heterogeneous polymers or anything like this. Okay? And so my claim here is that we are not going to input a priori adaptive mechanisms, but nonetheless, we're going to see something that looks like adaptation from the mathematical perspective. So the questions that I'm going to address, are, first off, so under all of these kind of considerations, could we actually find information limited observables, like measurables? Something that is bounded by information theoretic terms. Okay, so that's the first question. And this second question is kind of spoiling the answer. Like, can in these cases some kind of memory phenomena emerge? Obviously, the answer is yes, otherwise I wouldn't ask the question. And finally, I'm going to also, I already mentioned this already, but I'm also going to insist that these sort of constructions, at least in principle, can be empirically accessible or plausible to do this in the lab. All right? Okay, cool. No questions? I'm going to move to the actual meat, but as I promised, I'm going to first go through a slight detour. And for that, I want to ask you for a raise of hand question, which is like, who here have heard of Kelly gambling? One person, two people. That's great, actually. I give this talk like a couple of weeks ago and also asked this question. And this is a kind of like, so far the statistics seem to match. And so this is good. Kelly gambling is kind of an interesting story in itself. And I am going to just explain it to you in the most basic case, all right? I'm also going to say why is this inspiring for the kind of work that we did. So who's this Kelly? So Kelly was actually a colleague of Shannon at IBM in the 50s. And you have a question? No. And he was quite peculiar. He liked to drink a lot and smoke a lot, and unfortunately he died very young out of that, probably. And he loved going to the horse races, which is why actually there's the whole story is out there for you to read. And he very recently, after the publication of this seminal paper by Shannon on the information and communication systems, etc., he was like, "Oh my God! Like, can I actually figure out a different way?" Well, he basically came up with a different way, a completely kind of orthogonal way of figuring out the role of information in a kind of a slightly different context. And the context, actually, surprisingly, is gambling, right? Gambling in horse races. Let me explain you how it works. Suppose that you have like some amount of dollars, some capital. And then you're going to a horse race, a very simple horse race, only 2 horses. And horse red here is going to win with probability P, and horse blue here is going to win with probability Q. And then you want to allocate fractions of your total capital, right? As a bet. Like, I don't know, if I have $100, maybe I want to allocate 30% of it on red and then 70% blue, whatever. This will be our like, optimization variable, like the free variable. And also suppose that you go to the house and you're going to do this betting, so they are going to give you some return, right? So for each dollar you bet on the red, if you win, you get 2 or 5 or 1,000. Okay? So this is like your variables here. And then let's suppose there's a random variable, I call it epsilon actually. Let me say why I call it epsilon. I call it epsilon for environment. So already I'm hinting at what's going to come next. Environment here being the horses. Which environment is going to be the winner? Which horse is going to win? Right? Which environment is going to appear is which horse is going to win. Maybe I'm being overly slow here. Please tell me if I'm going too slow. But the point is that Kelly asked the following questions. Like, if I keep going to the races all the time, and I want to just maximize my long-term growth rate of my capital, that would be this W here. And then would just be here an index of the number of the index of the horse race that you're gambling on. If I want to maximize that, what do I have to do, right? And if you do the calculation for this very simple multiplicative process where you keep growing your capital as you do your bettings, right? This is your actual answer. It's quite straightforward to prove. It's something very nice and simple. But notice that this is yet without any kind of optimization. This is just like, if you ask this question, this is your long-term, this is the limit for finding W. I'm sorry. Okay, and now we notice that there are 2 contributions to this long-term growth rate. The first contribution here, interestingly, it's independent of the bet. It doesn't have anything to do with how I allocated my money. It does have to do with the return rates. These are very simple calculations, by the way, but notice something interesting is happening already, that this is decoupling nicely, right? The next term here appears with a minus sign, so it's a cost. It's something that I'm paying. I mean, I'm not paying, but it's something I'm not getting because of this term here, right? And it's interestingly, this is the cross entropy. So this is just P log B if you want. Given that B is a fraction, you can interpret it as a probability, right? And so if you want now to establish, okay, how do I maximize this? Something that looks very trivial, but at the same time is a bit surprising happens. The cross entropy can be written with a Kohlberg-Leibler diversion, right? And it's always going to be bigger than the entropy part that emerges from this decoupling. And actually, the Kohlberg-Leibler divergence can be minimized, and it's minimized by this condition, right? Which we call the optimal betting. In finance, this is often called bet hedging. Somebody was a question?
Yeah, sorry, it's just that the bold P, is that both P and Q, or?
Go again.
Yeah.
Bold P?
Bold P, is that the P and Q of the red and blue horses, or is this just P?
It's a P and Q. Bold P is the vector PQ. Sorry, yeah. Maybe the notation is a bit
So it's the vector.
clunky.
Okay, all right.
I don't know if I should write it. It's just P, comma 1 minus P. Actually, Q is 1 minus P because in the
Yeah, that's
example.
just two. Sure.
Yeah, sorry. I should have been more clear. This is the vector, right? That's why it's in bold.
That's fine, that's all I know.
Thank you. Yeah. But this is clear, right? And now this is our like optimal strategy. And you would say, like, man, that's kind of like underwhelming. The optimal strategy is just like, bet as the probabilities, equivalent to the probabilities of each horse winning. Yeah, but notice something kind of weird here. This is completely independent of the return rates. So if I had like a crazy return rate, right? Like, I don't know, you get $1 million if you bet for horse red, and then you get $1.2 if you get per dollar if you get bet for horse blue. Still, this optimization problem tells you don't care about that. Just look at the probabilities. Of course, the caveat here is that you're doing this at the long term, right? Otherwise, this would make no sense. All right. Cool. Notice as well that the growth rate is now the optimal growth. The optimal growth rate is now given by this, where you have this entropic cost. But actually, if you read Kelly's paper, which is very easy to read, by the way, and it's very, very nice paper, he started directly by considering something else, which he calls site information. I think in machine learning, some people here from machine learning, I think that somebody once told me, oh, this in machine learning is called latent variable. I don't know if that's the case or not, but I'm not an expert. But what I mean by site information, that's what he called this extra variable, extra random variable. Site information, it could be anything actually. I don't know. You can think of somebody who's like in the house and he knows something else. I don't know, and he's behaving in a certain way, and you're observing it from the place where you see the horses, and you're like, oh, I think this guy is gonna. I think this guy is betting for the red, so I think I'm gonna tilt my bets towards the red according to the kind of information that I got from him. Already I'm using this kind of language, and that's kind of spoiling what's going to happen next, which is if you use this site information variable and you do the same calculation, you still have this term here that has nothing to do with the bet, neither with the site information. It's just the same term as before with the marginal of the environment, so P and Q in this case. And here you have the entropy term, but now the entropy, the cross entropy term comes with a conditional entropy from which horse is going to win, condition on the state of the random variable. I'm sorry, on the site information variable y. And here, what you can do effectively is, okay, I'm gonna place my bets, but conditioned on this site information variable. And if you do the same calculation, now the bet hedging strategy, which is this optimal strategy for long-term growth, it's gonna look like this. So instead of having, the probabilities match, you have the conditional probabilities match. And you interpret this fraction, which you are allocating capital, as conditional probability. And something interesting is happening here, right? Because now if you look at the maximum return rates, long-term return rates, or whatever you want to call it, in the case where you have site information, and in the case where you don't, the previous case we saw, and you just like compute, okay, what's the difference? How much? So if I'm at the maximum with site information, and if I'm at the maximum without site information, what's the difference between these two states? Turns out to be exactly the mutual information between the random variable that determines which horse is going to win, and the random variable, which is this site information. And so all of a sudden we have almost amazingly, we have like and perhaps more easily than going through all the painstaking way of like looking for like how to understand channels and so on in information theory. Here we already have this nice result by actually looking surprisingly at horse counting, right? And I don't know. I'm really fond of this, even though maybe it's just I don't know, a quirk. But the point is like, okay, so by the way, this is sometimes called operational information theory, because the idea is that somewhat this feels, at least from a physical perspective, this feels more close to a tangible thing, because capital, even though it's not a physical measurable if you want, or you can argue about that, I don't care. But capital is something that you could definitely measure much more succinctly than, I don't know, the channel capacity of a system, which is something that you can also do, but it's much more complicated, right? And here we have like a connection between what I would call a more physically or directly physically measurable by virtue of thinking about total capital, and yet, or total capital growth. And yet already this is giving us this information field terms. And the whole spiel about this Kelly, which I hope at least this was interesting to you guys. If something good comes out of this talk, is at least you have now heard of Kelly gambling. The question is now, okay, can I actually devise a way where you can make this possible to be applied in chemical reaction systems, right?
Can I have a question?
Sure, of course.
So y is the latent variable, right?
Yeah.
But can you infer, or do you have access
Yes.
to the distribution of y?
Wait, what?
The distribution of y, because y at the end of the day is a random variable.
Yeah.
Would you know what is the distribution of y?
So this is the story, right? Y could be anything. Of course, you need to have access to this variable, otherwise you have no access to site information. In general, you would have like some py if you want. The more general thing, you would have like p ey or p epsilon y, right? And you can marginalize if you want and have py. Yeah, sure. If that's what you're asking, I don't know.
Yeah. Thanks.
I mean, maybe it's not the case that you can do that, but if you cannot do that, you really have no access to this variable. I don't know. I mean, these are going to be now perhaps more clear when I work out on the example that I show exactly what is y in that case. But I want to make it something very clear here. Y could be anything, right? it's a side, it's like what you call a latent variable, like side information that it could be correlated in different ways, or even,
More conceptual question. So in the beginning of your talk, you started to talk about semantic information, which I think of as really outside of Shannon information theory.
Yes.
Because it's adding value to the bits. This is totally within Shannon information.
and I'm not going to talk about semantic, I maybe should have made that clear. It's just like, that is like kind of the umbrella where this sort of project came from.
Okay.
You're completely right. I am not going to, okay, so here's let me state it differently, if I may. The question of semantic information was perhaps put forward in a formal manner by Kolchinsky and Wilbert in 2018. Other people have worked on this actually, so it's not just them, but okay, I refer to them. But what I wanted to highlight from that is like, okay, what really is interesting to me is thinking about the relevance. The relevance part. They kind of devise an algorithm to do this in general.
Mhm.
And perhaps with this, what I want to show is that information can also be relevant in different contexts and can actually, constrain your system. And you don't really need to go through all these it's painstaking. I know you know that process, that semantic information paper way of doing things, because you really have like to scramble all the degrees of freedom of the phase space, and that could be computationally impossible. And here in this setup, at least, maybe the point here is that there's not just one way of looking at this, right? And in this setup, my claim is going to be that you're nonetheless going to have information constraints without going to this framework. But I think it's a very good question. I thank you for pointing it out, because I should have mentioned, I'm not going to use that framework. So apologies for this. Yeah. Okay. That was the digression. I hope that you like it. If not, I'm sorry. And now I'm going to go to the general setup that we actually implement. But it really is so much inspired by Kelly that I think it's useful to keep the analogy going. Actually, our setup is, at least the first setup that we implemented in trying to address this question, it's actually very simple, right? Suppose that you have a flow reactor, continuous flow reactor. What is that? Well, it's just a reactor, which is often like well stirred and shaken or whatever, like you make it well mixed, okay? And you have some reservoir outside that you keep at a constant concentration, mass concentration. I always use mass concentration throughout this, okay? So you won't see stoichiometric coefficients. Anyways, the point is that you could do that as well, but it gets more complicated. So you have an external reservoir of precursor molecules, which I call A, all right? I'm going to give a particular chemical example later on of what could work as a precursor molecule, what could work as the replicator molecule. Okay, but so far, let's keep it abstract. And then they are just replicating at some rates, eta I, okay? Inside the reactor, you have these replicators and they just keep replicating. And then, interestingly, you have the outflow. And here's where you can measure things, right? In particular, you can measure how much total replicators are flowing outside, right? So I got to define these variables here. There's a very simple continuous variables. These are the concentration of replicator I, right? There's going to be n of these replicators. And big X here is just the total concentration, mass concentration of replicators that are in the continuous flow. You know, the nice thing about continuous flows is you can very easily produce steady states, non-equilibrium steady states. And we're going to work with this idea as well. Now, for the ecologists in the room, I've been told that somebody is an ecologist or has worked in ecology. This is actually very simple. Very simply, you can prove that for this simple setup, there's going to be an effect that it's known in ecology as competitive exclusion, right? Because assuming that all of these replication rates are different, in this instantiation, there's going to be one maximum value for replication. This is kind of simple, right? And this we're going to call it the winner replicator. I'm already using kind of the jargon from Kelly, but allow me to do that. This makes completely sense as long as there's no neutrality, and there's always a little bit of a difference between the replication rates of this reaction, the kinetic rates of this reaction. Essentially, there's going to be an index, right, which corresponds to the maximal eta. Now I call this the winner replicator. Okay.
You have a mu on the top. What is the mu?
Mu is the reservoir concentration, mass concentration of the precursor. Yes, sorry. It's just this is to give units to the whole thing, right? Yeah. In fact, if you make this, instead, if you want to make it such that you can be close to steady state, you can start initial conditions such that the total solid here is equal to mu, and you will have flow, you have non-equilibrium, but you will have a condition that is going to help you take some things out in the equation. But I'm not going to delve into that much, but it's actually really here, by the way. This is if you set this initial condition to the total concentration of the reservoir, then you're going to be able to kick out a bunch of terms on the main observable that I'm going to introduce now. Maybe I'll tell you exactly where these terms go away if you want. But yeah, it's just a concentration. I want to now focus on this part here, which is the introduction of productivity as a measurable. Remember that one of the key ideas here was like, okay, I want to have like a measurable that I really can do in the lab. Because long-term growth rates, for if you're betting or something on horses, maybe it makes sense. But if you want to see these in chemical reactions and you want to tell some chemist, hey, can you do this experiment for me? You're going to require, like, can you do, what do you want to measure, right? And so this is actually a measurement that can be done very precisely in chemistry, which you basically study production, sorry. So basically you look at what's outflowing over here, but then you can do an average over time of what's being outflowing over here. Yes?
Well, now you have two, the inflow and the outflow, and you both denote them by the letter phi.
Sorry, yes. This is the outflow rate, this is the inflow rate, and I should have said they're set identical values. These are one over time units, right? It's just the rate, and this is also experimentally accessible. That's a very good point, yeah. Yeah, really, you could set this to 1 actually. It would make things a bit more nicer, right? If you set them to 1 so that you fix the units of time, you can set this to 1, this to 1, and so on. Yeah.
Or just like you try to visually try to reach this equation, that they can index like phi I and phi out or something like that.
I'm sorry, yeah, I don't know. You mean this?
Yeah, so you have these phi's here. So if they would have an index, then at least for me visually it would be nicer, but it's just
Actually, we don't. Okay.
yeah.
I don't know if I rewrite these equations at that point, but I actually will allow. Okay, we are in the first steps. All right. I don't know if my time is already screwed, but
Take your time.
but you can actually have some freedom for this phi as well. So, for example, so far I'm just like thinking about one instantiation of this experiment. But of course, I'm going to be thinking about fluctuating environments. So I'm going to be basically setting this experiment like in an ensemble, right? And then you take averages. In that ensemble, you could, for example, for the different environments, you could set different phi. So phi could be dependent on the environment. So you still have some freedom here. Nonetheless, I make this for simplification arguments because this way, it's very easy to figure out the whole flux.
Yeah, sure.
Yeah. But sorry maybe I should spend more time explaining which parameter is which. Yeah. Let me go to this first then. These are going to be the very simple boiled down ODE system that I'm going to use for this first kind of non-fluctuating nothing environment case. But this is an important one, right? Productivity. If you see what I'm integrating out here is just the outflow of the total number of replicators. This is something you can measure. And then you just integrate over time. Tau is just how much time are you spending doing this experiment since you started, right? And then you just do this coarse averaging. And that's what we call productivity. So productivity is a rate, right? It has units of 1 over time. Okay? Because this is also units of 1 over time. You see right here. These units will go away. These are going to be constant. So basically mass concentration over time. Okay, and that's going to be my observable. This is an observable that is not so uncommon. And if you think about it from the engineering perspective, it kind of makes sense. If you want to have a reactor and you want to produce stuff, this is one of the things that you would look at. All right?
Sorry, can I just ask a question?
Sure.
So those two equations you have there, do they come from the chemical reaction
Yeah.
that you had before, or
Yes.
you added another one?
I'm sorry?
Or you added another one without telling anyone?
I have not added another one. Okay, if you think about the input and output as other chemical reactions, I should have added them.
Ah, okay.
Formally speaking,
Okay.
I think it's clear from the picture.
Okay.
But it's okay. If you want to be formal, you should add as well that you have input at constant rate phi
Yeah.
from the reservoir, which you keep at constant mu of precursor. That's why you get these terms. Mu phi,
Exactly.
right?
Yeah.
And then you have outflow of everything because it's well stirred. So yes, if you want to be very precise and write the chemical reaction, which you might want to do if you especially want to, go into stoichiometric matrix and so on, then you should have added that. Other than that, the rest are just,
You added the equation, so it came from somewhere.
it came from somewhere.
All right.
Is it clear now though?
Yeah, it's clear. That's one reaction that should have been written.
Two, in fact,
Yeah,
right?
sure.
Well, actually, 1 plus n plus 1, right? Because all the others,
No, yeah, there's.
all flow
That's
outside.
only I think.
Yes, sure. Yeah, you're right, you're right. Please, more questions, maybe. I'm happy to get all these questions. Okay. Then I'll move on. This is actually what you get for this simple case. I mean, here again, I'm just like having one instantiation. I give you a bunch of eta i's, right? And I just like run this. And in fact, this is an exact solution. I don't have to do anything. There's no approximation so far. This is your productivity. You can compute this exactly. It's actually a fun calculation, but it's very simple. It's not sophisticated. And in a sense, it's like an extension of what Kimura did, okay, in the 60s. But he was looking at alleles, and there was only 2 species, and there was no concept of a precursor and so on. Nonetheless, you reach kind of the same philosophy. You reach kind of the same sort of, 2 contributions, and one looks like a log. That's why I use his nomenclature for what I'm going to show here is what's called substitutional log. This substitutional log term really comes from Kimura, and he was thinking here about species, competing for survival without any notion of a resource or actual chemical reactions. Okay, and I'm going to explain to you what it is, just for us to understand this very simple thing that is not even, I don't even call it a result. This is just a step towards what we want to find, right? So first off, when we start the system, importantly, we start the system at some, relative distributions between the different species, right? And that's actually something that maybe we can think of it as a preparation of the system. Interestingly, when you compute productivity at time tau, remember productivity is the average, or 1 over time average, right? What you get here is that the result only depends on the winner. Remember, R is the winner species, the one that's going to outcompete everyone. Okay, and this is an exact result. There's no tweaking in here. Interestingly, if you think about production, not productivity, but production, like how much you are, like if you had like a bucket outside and you then start like at each time step, I don't know, you measure how much is in the bucket, not in the flow, but in the bucket. That's just after the flow, you would get the total production of Replicator. And what you see is that initially you have some trend, right? And then this trend gets corrected. You see how the actual production curve kind of gets corrected, right? And it acquires the slope of what I call would be the optimal production, right? How you would be optimally producing. And optimally producing in this case, it's something very simple. It's just like if you were, all of your reactor was filled with the best replicator from the start, you would have been optimally producing from the start. That's this blue line over here. And that would be, well, in this unit, I just made it so it's equal to 1. That would be the productivity, the optimal productivity, right? And what you see is that the actual system actually, in this case, you can have these kind of shapes for the color, but it will go down a little bit due to the preparation being not well suited, right? Maybe you have put the initial condition for the, for the best replicator at a very low concentration, and then you have like kind of this payoff, and finally, eventually, at steady state, you're going to reach optimal probability. This is also, you can see this also over here, because this tau here, if you take it strictly to infinity, this is going to go to 0, right? And you are going to reach steady state productivity. Sorry.
So in the context of this equation, A plays the role of Y, right? The sign information, the Latin variable.
Wait, what? A?
A, yeah. I mean, I just want to make the connection with the.
I'm going to make this connection. This is the whole point. But you mean A?
Yeah.
You say? No.
It's not.
No. Let's not get ahead of ourselves. The side information is going to come up when. I mean, again, side information could be anything. I could cheat and tell you, hey, look, I prepared this so that this is going to come up next. Then I am the side information, and you're going to do excellent, right? So it could be anything. But in the context of the experiment that I will explain to you, imagine an experiment is going to be something to do with kind of an intrinsic memory pattern that comes up. But let's not get ahead of ourselves. Maybe I'm being too slow. Please, guys, tell me if I'm being too slow. But I'm happy also to answer all of these questions. Maybe it's good to clarify a few things. Okay, obviously there's going to be a productivity increase, right? At the beginning, we don't have a very good productivity, and then at the end, we're going to have a much better productivity once competitive exclusion has taken place. But notice here, this is kind of an interesting, I don't know what I did. Did I do something?
I have touched twice the screen.
Double tap.
Double tap? Okay, sorry. Because this log term here is kind of suggestive, right? It feels like a little bit like what we saw with Kelly, but it's perhaps not very complete here because these are concentrations, but they're mass concentrations. They are not really normalized at the moment. But we actually do normalize, and we assume that you don't have to be exactly at steady state, but you assume that you're close to steady state. Okay, this is basically our main assumption. As a matter of fact, I think that I didn't write approximations here onwards, and I probably should have. But let me just say that if you assume that you're close to steady state, you can decouple this in the following way. First off, this again just as before, when I write star, I mean these are the values of steady state. And notice that before you don't really have to be at steady state for this to come up. They come up. All right, this is exact for any tau. But I'm going to now assume that you're close to steady state, not necessarily at steady state, but close to steady state. And then you can rewrite these things in the following way. First off, I introduced this, sorry, let me put it all so that it's perhaps clearer. Okay, these are just like the steady state values. And I'm just like introducing the total concentration at the beginning of the experiment, the total concentration of replicator. And this is going to act as a normalization factor, right? And now notice that I can just like take out the logarithm into two parts. And it's simply under the steady state assumption, what you can write here is that, okay, this term here, which appears here perhaps as a cost, suppose that, you know, it is a cost, but only depending on the initial conditions, as a matter of fact. But if you think about this, and you consider that at the initial time, for example, the total concentration of replicator is low, this is also going to be negative, and this is also another cost due to the proportion of the winner replicator that I placed in the system. I'm only concerned about this one, actually, right? Even though when I want to study the full-blown correlations, I'm going to have to study the vector of Q, okay? And that's a cost. And it's a cost that is in logarithmic form, so it's already suggested, right? It feels very much like the Kelly story. Okay, I mean, maybe before we go on, maybe there's some questions. Otherwise, I'm going to just jump ahead to mathematics. It's not so complicated, actually. And if anybody of you want the details, I'm very pleased to send them or write them down for you. But the point is that from here, we can now move to the main results. Okay? Which are going to involve thinking about fluctuating environments, right? So far, I've done this exercise here. It's kind of like a neat exercise. It can be done by any undergrad. But now we can think of something a little bit more interesting, which is like, okay, suppose that you're really thinking about this from like a fluctuating environment perspective, where you have like many different possible choices of the eta I parameters. Remember, the eta i's were the replication rates of the autocatalytic reactions, right? And this is just a depiction of how this would look like. I don't know. You have like some conditions with which the environment will be hit, or the system will be hit, right? And I'm at this moment abstractly I'm terming them 1, 2, up to m. I don't care, right? And under these conditions, maybe I choose a different winner. Maybe the eta i's are moving so that the replicator variable r is actually also random, right? And it's going to be presumably it's going to be connected to which environment is going to be chosen. So basically, I'm generalizing what I had before, but adding this variable for a random environment. Okay, which you can, let's think of it as like you have infinite resources, so you just set up this system many times in your lab, and then you assign with some probability distribution, you assign different environments at each of these reactors.
So you assume that your eta i's are functions of the environment.
Yes. Yeah.
Okay.
Yeah. And it could be anything, right? But the most important thing, however, will be that you actually want to know. See, this it may be very small, but this is r of epsilon. You want to know at each environment which is going to be the winner replicator. That's the important kind of bit of information. pun intended maybe, that's gonna come in, right?
Yeah, but here function of the environment means what? Function of some, what exactly?
I'm sorry.
Function of the environment means what?
Look, I'm gonna give you the example that I wanna work out next. You can have chemical systems that are susceptible to light intensity, and they're actually strongly susceptible to that. They're built up, they're synthetic chemicals, and they exist in the labs. In Denmark, actually, this is Schiesbrand Otto's lab. I don't know if you guys know. But the point is that you can have a replicator that if you hit it with, in this case, they have like a light intensity wave, like not wavelength, because this is not wavelength, it's like, a bandwidth, right, of intensity. One replicator is going to be favored and the other is not. And if you hit it with another bandwidth of intensity, another replicator is going to be favored and the other is not.
All I meant is, you're gonna make these rates functions of some other dynamical variable, or you're just gonna fluctuate these rates with some distribution of some.
With the distribution of environments. But in this case, this is very simple, right? It's like, if you're in environment A, this is an extreme case. If you're in environment A, basically all the etas are going 0 but 1. That would be the more coarse approximation. It's not exactly like this. It's in proportion, right? But that's an instantiation, an extreme instantiation of what I'm going to do.
So it's not time dependent, it's a fixed distribution.
Ah, man. Wait for next.
Okay.
Because yeah, let me just say the following. This is a bit unrealistic, right? The whole point was to make it realistic. You cannot make 1,000 reactors. That's kind of like bananas. So we're gonna try to do it in one reactor. When we do it in one reactor, we're gonna let the environment change over time. And that is going to select different best replicators, but with like some kind of cyclic process. But this is the next one. Yeah, fine. Oh, sorry. You sure?
Yeah, it just seemed to me like it's not that hard to make replicators, so you could have lots of environments. I don't.
Yeah. For me, it's crazy that people do that. Like, I'm
Appearance.
Yeah, I'm amazed that this is like possible. And actually, it's been done for so long already. Like Monkey Oxford already started with this. It's an amazing field, and I really have a lot of respect for the experimentalists there. And also, they have a lot of insights in questions of evolution and so on.
So-
Sorry for the digression.
Yeah, so there's typically like in these systems, there's two sources of fluctuations. One is like the rates. I think in ecology, they even have names for this one. And the other one is demographics.
Yes,
Stochasticity, but you're not putting.
I'm not, but I mentioned them at the end.
Okay.
But yes, I'm not. There's a very good point. And to do that, I mean, I will mention this at the end, but to do that, you will need to go to a master equation.
Yeah.
And actually, this is what we want to do next. Yes.
But even,
But this is a very good point, yeah. Go ahead.
but even in your system of ODE, if you're now thinking about fluctuating environment and fixed, not changing over time, then you basically have the random coefficient. So either as you said, and then you can
Okay, I see.
you can use the same method for the generalized Volterra model, like
That's a very good point. Yeah.
or tackling this problem directly.
Yeah.
That is a very good point indeed. And so it would be different from the kind of approach that I'm doing, but
Mhm.
I wonder how information measurements would appear there. Because
No,
I'm
but-
familiar with the generalized random walkout Volterra, but
At least you can get the distribution of
Yeah.
the species, right? And then at
Yeah,
the
yeah,
end of the day, you are interested in advice, mutual information. So
maybe it's differential
If-
entropy measurements,
if
right?
you know the distribution, the joint distribution
Yeah,
of
yeah.
the y and of the p and in your formula or epsilon, how you call it, then you can compute the mutual
That's a very good
information.
point. That's a very good point. I didn't think about this. I was thinking about like discrete environment states, right?
No, but even this can be discrete, it can be continuous environment, does not matter,
I
because
see
at
your
the
point.
end of the day, you want to know the statistic of the environment. So the
yes.
first moment, second moment, and so on and
Exactly.
so forth. And then there's some proven theorem about the universality class.
Yes.
So as long as the higher moment fall off fastly,
Yeah,
the result will be depend only on the first and second moment.
that's
And it can be
Boolean paper, right?
not specifically Boolean, he just how to say rewrite the things that have been known in the 90s.
Okay, good to see, good to know that. Maybe we should talk about this later, because I think this would be a very interesting just a step forward. But yeah, I didn't think about this, that you could use the logical generalized equations for that. That's a very good point. Thank you, Tuan.
Because this is the connection they pointed out. So the Lotka-Volterra dynamic is the n+1 dimension of the replicator dynamic.
Yeah,
So this is the corresponding.
yeah, there's actually in a way, the way that you get to the productivity result and so on is the same transformation that you're alluding to, I think, which is this, where you go from like these nonlinear equations to like, this was done in, I don't know if you're referring to this, but I mean, this is a technique to go from these nonlinear Rotkotter equations to something linear. This was done by Suetin and Schuster in the 80s as well. But I don't know if you're talking about that.
No, I talk about as a work, but anyway, there's a one-to-one correspondence between the replicator dynamic and the
Yeah.
model.
That's for sure. Yeah, so that would be very interesting. Maybe we should talk about this later. Yeah, that's a very good point. Thank you. Great, great. More questions? Okay, awesome. So basically, we've just like gone from like a single reactor to multiple reactors now, and we also allow for this site information. I've not specified exactly what the site information is now, but again, it could be anything. It's just like some preparation recipe that you can follow, right? Or some kind of like view of what the system is going to do, right? And you can condition all the preparation that you make on that site information variable. Of course, that's also going to be conditioning the initial state of your total total concentration of replicators. That's why it also appears there. The rest, the index variable epsilon is just stating that this is done in different environments, right? The chosen environment with some probability of environments and preparation, or environments and site variables, right? Okay, I already jumped to the main result here. There's a few tweaks that one needs to do to arrive at this. Let me just state the general idea behind it. First off, we here observe there's going to be, the average. I'm looking at the average productivity. So I'm looking at the first one. I'm not even looking at the second one. Okay. Again, this is something that I want to pursue after.
And this is averaged across realizations of
Yes.
your environment.
Exactly. Yeah. Yes.
But
It's average about over this distribution, which is the distribution of realizations. Yes.
it assumes that we know the distribution of the environment.
Yeah.
Okay, yeah.
Yes. You can, I don't know, you can set up a nice code where you choose environment or whatever. Yes.
Does this show somewhere your equation? I mean, if you have a T of Y, T of.
Yeah, it's actually inside here. I'm gonna show a bit of some of these terms, but I want to get something across quickly before I do that. Okay. Actually, I can show you all of them in an appendix that I added here, but it's a bit cumbersome. But also, I can work with you later if you want to see it, or I send you the draft. Okay. Whichever. But I want to come across something important here. These corrections here are cost terms, right? I'm going to unfold them next, but I want to emphasize that they depend on a different distribution. They don't depend on P, they depend on this distribution pi, also this cost term here. I want to give you a little bit of intuition what this distribution pi is about. And this is just tweaking with the math. You reach these values. I'm going to unfold these terms next, but let me just give you an intuition of what pi is. Okay, pi is a distribution that is related to P. P again is the distribution over the realizations of the environments. Okay, but we're going to redefine pi using P, but biasing towards the slowest replicators. So this distribution pi is kind of a tilted distribution from P again being the distribution of realizations, and it's biased towards the slowest replicator. And there's an intuition why is this the case? Why do I need to focus on this distribution pi rather than P? And notice the following, it's kind of fun. Like if you think about these replicators, right? And then you're preparing the system, you really need to be very careful about having very little slow replicators in the mix, right? And what do I mean by that? Slow in terms of like, not in relative terms, but in terms of absolute terms. Because suppose that I have an environment that chooses the slow replicator, as long as in time scale, and then, makes all the other replicators, this would be an extreme case, makes all the other replicators effective eta go to 0 or very close to 0. What's happened is that if you make your preparation in a way where you kind of downplay these slow replicators, then you're going to pay a high price in order to reach, because this slow replicator now needs to, be removing all the other replicators from the reactor. And so this is an interpretation of something that comes out of the math. So this pi distribution, you just work it out. But it's interesting to see that it's biased towards the slowest replicators. And so that's something that I wanted to mention. Again, if you want exact expressions for this, I can show them to you. But at the moment, I think I want to focus on this form here. This from here to here is just taking averages over P, E, Y. So there's no magic involved. Okay. The other thing here is this constant omega, which is going to be a global constant. It's related to the number of replicator events per unit time. It's kind of like, an overall constant you can put out. Let's actually explore deeper what are these cost terms here, right? And I call them cost because there's a minus sign here. Even though we're going to see now, some of them are not exactly costs. This is the main result of the paper. So please, if you have questions, I'm very, very happy to answer. I think that maybe, perhaps I'm wrong, but maybe what you were saying is like, oh, but what are these observables? Where is P showing up here? P, remember, is like related, pi is related to P. So P is already embedded in pi, okay? So there, it's here and it's here, let's just say. But in this term, it's just directly the same as you would do. Like if you have a steady state, you would just average over environment. And you don't even, here again, similar to K, you don't even involve the latent variable, the side information. It's just like this, okay? So this is going to be the steady state average, which is independent of the side information. That's the first term here, which if you want is like kind of like, if you were thinking about this kind of in an efficiency kind of manner, right? This would be your Carnot efficiency, and these are like your payouts, right? Like this is what you're paying. You're never reaching this value. Okay. Maybe that comment was a bit weird, but if you work in thermodynamics, this makes a little bit of sense. This term here is similar to what we had before, but now notice that I need to average. It separates nicely into these averages. One is average over the marginal of pi for the environments, and the other is average over the marginal of pi over side information. Okay. For example, if you have no side information, this is going to be just the preparation that you make, because it's not dependent on the side information. But in general, it will be, and this is, I call it a cost really, but you could perhaps make this very large. If you make this very large, it's actually a benefit. It's rather than a cost. Okay.
That shit is positive, and because there's a minus sign, and that's already a minus sign, so minus.
No, because this is a constant. Yeah, I mean, in reality, the units here are canceling afterwards, but this is perhaps this is not the best way of writing this. But I prefer to write it this way because this way you can separate this both. But these are, this is kind of like wrong in a way because the units here should be perhaps written down. This is not a unitless value, and it's not so X here is not like a value from 0 to 1. It could be above 1. That's a good point because these are mass concentrations. It's just that, I should have written here divided by, I don't know, X circle or something. Do you see what I'm trying to say? Of course, the log cannot have units.
You probably.
But it doesn't change the sign of the term. I don't know.
Well, yeah, but you can. But this term is minus. Yeah. But this term is minus as well. That's
Yeah, so it's a plus. So it's always.
Oh yeah, except if you have a very low concentration. If you have a very low concentration with respect to the unit that you're using. So if you have a very low concentration with respect to this is going to be it's going to be, I don't know, if you have a very low concentration with respect to the units that you're using, this is going to be a cost. Yeah.
The difference is going to be the cost.
The difference is going to be the total cost.
Yeah, sure.
Yeah, that's the correct way of saying it. Maybe this is not the best way of writing it, now that you mention it. I will make sure to change this.
Well, I'm not sure if my question should make you rewrite your paper.
No, not just this part. I actually realized that I don't like, I thought I was more focused on trying to separate things. I realized this actually makes no physical sense to write things like that. Nevertheless, this is perhaps not so interesting because the idea here is that you are arranging your bet, right? What you're doing is you're placing the best bet so that you maximize productivity. And this is completely independent of the bet. Again, the bet being the fraction of initial concentration, fraction of initial concentrations for the different replicators. Okay, the Q distribution. Do you have a question? No.
No.
Okay, I'm going to explain this now, right? And this comes in this comes in.
Just double tap again.
I'm so sorry about this.
Double, yeah.
This comes in within this cost term here, which is actually the interesting term. This term unfolds into three contributions, and perhaps this is not surprisingly very, very akin to Kelly's. The only thing here is that you have had to work out exactly the expression for pi in order to do this property. So this is the entropy, this is Shannon entropy for the now random variable, and this is interesting from what you said before, but anyways, from the now random variable R, which essentially means the replicator that's being chosen, right? Again, for each environment, which is already distributed according to some here modulated by pi sub e, you want. You can actually marginalize for pi sub r, and then you get this entropy contribution. In a way, if you want to interpret this, it's kind of like a cost of identifying for the system. It's kind of a cost of identifying which is the fastest replicator, given your example. Then you have this interesting cost here, which is again the KL divergence between the conditional entropies. Perhaps this is not so surprising given what we've learned from Kelly, between this pi distribution and your preparation, your conditional pi distribution over replicator's condition on y, and then the preparation, or the fraction of the different of the winner replicator condition on y. Okay, so how do we interpret this? It's kind of a cost of preparation. It's kind of a cost of accuracy. How good are you preparing your your reactor, right, in front of this random event that's going to come in the random environment and so on. And finally, there's a benefit. This is definitely a benefit cost. This is always going to be positive for sure, which is the mutual information between these two random variables now. The choice of test replicator and your and your site information. Go ahead.
Well, so the best replacing is the initial condition that's being prepared, and then the environment is stochastic, so we don't know exactly what is the best thing. But so just thinking about it, just forgetting about initial conditions, you let your system run, you get into some sort of stationary distribution in the end.
Yeah.
What if I just take my initial condition to be the stationary distribution?
But that's for one run, right? That's you chose an environment, and then yes. I mean, if you only have like.
But if I know the environment, then there is no stochasticity, so then there is no distribution. So
I'm sorry, what?
If you do one run, your environment is fixed.
Yeah, but I'm not doing one run.
That's what I'm saying. So you have for each realization of the environment,
yes,
there is a winner.
Yeah.
And so you can just, given the distribution in the environment, to get a distribution of stationary states at the end.
Yes.
And now I just choose my initial condition to be drawn from this stationary distribution.
Yes, I think that's what you're saying.
And that should be, is that the optimal thing to do?
Yes, that's the bet hedging strategy.
Okay.
Right?
Yeah.
Yeah, perhaps it's unsurprising, but this is the result from this analysis. Essentially, what you're saying is true, and that's what kind of Kelly came up with when he was trying to maximize, in his case, long-term growth of capital. And here we're thinking about maximizing this cost term here, and notice that I've made it in a way that, first off, it's interesting because it gives us all this information, theoretic measurables, or maybe I should say functionals, okay? It gives us all of these, but this is the one that's dependent on Q. And I think what you're saying is essentially correct. And that's the optimal strategy, which is making this zero. Approaching at maximum this pi. Let me just say that this pi is not so trivial. It's not exactly P of E, okay? No. You have to do some transformation. But once you've done this transformation, if your chemical system, I mean, okay, you'll see why I say this now. But if you are allowed, to make such a preparation, then you're going to be making this zero, and you're going to be at least in terms of preparation, you're going to be at an upper bound of productivity. Yes, this is the. I hope that everyone's following here. This is kind of like, let me say, the hardest. It's not so hard, but this is the most like a bit involved formal part of the talk, and we are running towards the end now. So please, if something's not clear, I'm happy to try my best to make it clearer. But yes, this is actually, I mean, this for me is probably the main result. Being able to write things this way and understanding this separation. Jordi. Thank you. Okay, so these are two bounds that we found, and very interestingly, these bounds are information theoretic bounds. And that's kind of like the crux of this project, right? To figure out whether there's something that really is bounding, in this case, simple autocatalytic chemical systems, and trying to figure out whether in reality these bounds can they be achieved? Are they like somewhere in the middle of nowhere that nobody cares, or is it something that is sensible to think of, right? And perhaps even empirically accessible. So this brings me to my last part of the talk, which is, okay, this has a little bit of a wrap up of what we have been doing, right? I mean, I'm gonna go a little bit fast here, but I hope that this comes across as obvious now. Like one of the things that we're trying to address here is like, okay, you have chemical reaction networks that actually we're doing it the bare minimum, like ODE system, like no complications, no master equation approach, right? And yet, I mean, we're trying to kind of parallelize this, or at least philosophically, with Kelly gambling. But you know, Kelly gambling is kind of a discrete event, right? You choose a horse, and then yeah, sure, you can always think about like an ensemble of environments. But at the end of the day, if you want to do this in the lab, you should have to have something that is much more realistic, and or I don't know why this is looking different, but they should be the same colors. This is probably a weird effect of Beamer, but I've never seen this before. I hope that the next plots show up well, because otherwise it's going to be a mess. But this should be two colors. What I'm saying here is what I'm going to now think of is perhaps connected to what you were thinking about before. I'm going to have just one reactor. I'm just going to set this reactor, couple it to some environment that it's fluctuating. And I'm going to make it in the following way. I'm going to make it cyclically, right? So here I'm in environment orange, okay? And then I am in what I call inactivity phase, right? I coined these two terms, activity and inactivity. And what is going to happen in inactivity is I'm just going to close the system and let it go to equilibrium, okay? For a while, just for some period of time. And in fact, and as I will explain next, you can do this and not even permit replication to happen during inactivity. And that's kind of a way, kind of an autonomous way for letting the system figure out a strategy for what's going to come next, right? And now the environment during the activity phases, these colored time frames here, is going to be changing according to some statistics that I can just make it as complicated as I want. It's going to be a chain, right, of ones and zeros if you want, and I can make it as correlated as I want over time. Okay, I'm just going to explore this set and see if I can apply all what we learned from before. Okay, this was another point that I already made, which is like the nice thing about these, and this is something like we want to motivate chemists in favor of thinking about this kind of experiment, is that you now have something that you don't have to look at unrealistic long-term growth rates. You can just like figure out how you're measuring here the output and have access to these productivity measures. Okay, maybe this is not pertinent at the moment. Let's actually talk about the specific system that we thought of that could be applicable for our formalism. And these are what sometimes are called photocatalytic self-replicators. And in particular, these ones were, as far as I understand, they were first found in last year. These kind of monomers have been known, I think, for decades now, maybe a couple of decades. But these are in chemistry they call them these are macrocycles that come from what is called a dynamical combinatorial library. What the hell does that mean? Suppose that you have this molecule over here, right? You can think of it as a kind of a monomer, right? But these monomers can attach in cycles. Like, I don't know, think about this one. I have this monomer that's touching, over these ends. This arrow corresponds to this part of the molecule, right? And you make this little cycle. And these cycles, they're interesting because they kind of match on top of each other, and they make these interesting fibers of cycles, right? In this specific case, here they don't explain, but they added something, in this figure it's not shown, but they added some extra stuff, a cofactor, okay? And this cofactor changes the oxidation level of the system and actually changes the whole kind of like local environment of each of these molecules, of each of these fibers, in a way that, and this cofactor, by the way, is the one that's photocatalyzed, is the one that depends on the intensity of light that's being hit to the system. That is going to essentially, if you have dim light, this is my sign for dim light, okay? It's not related, by the way, you're gonna see like red, again, green and yellow, but these are not wavelengths. This really is light intensity, plain as that. It has nothing to do with like a specific wavelengths. But this will be my sign for dim light environment, and this will be my sign for strong light environment. And what they show is that under specific chemical conditions, together with this cofactor here, which I just like depicted with this ball, what these systems do, they couple to the cofactor, and essentially when they are shed dim light, they are able to keep growing, keep growing, keep growing. These fibers keep growing, and then they break. And that's nice, because when they break, what happens is that now you have two new active locations, right? If you break from here, this is now going to be able to grow this way. And this one also. And then you have like exponential growth. So the way that chemists model these interesting synthetic molecules is literally by thinking about them from an autocatalytic perspective. So these are synthetic autocatalytic replicators. There's a few of them. There's not just these types of synthetic autocatalytic replicators. This is one that fits the bill for us. I think that's how we say it in English. Fits the bill because it allows us to discern these two environments, and so we can apply our theory. Let's do that. But I think you have a question, or you nodded somewhat. Yeah.
No.
Okay. This is just nomenclature. The one here, the bold one, means monomer, and this is like the examer formation. This is a collection of hexamers that are in the fiber state, right? And that's the one that you observe as being an autocatalytic replicator. And this is the source, the precursor molecule that you need to keep flowing into the system so that you have food in order to keep replicating. And this is the trimer. That's why it is 1/3, 1/6. This is just nomenclature from chemistry. Okay, these are trimers and hexamers. Hexamers are favored by dim light environments. Trimers are favored by strong light environment. So now we have all the elements that we need, right? Two species, a simple case, n equals 2. So now we need more replicators. And then we let the system go through inactive dark phases and active lit phases, either with strong or dim light. In the inactive phase, the cofactor also inhibits replication. And all you have is, sorry to go back, but all you have is this kind of like reshuffling. This is what experimentally observed, by the way. They did this beautiful experiment, and unfortunately we don't have, they didn't measure exact rates. So we're working with like kind of like wild guesses of trying to fit their data for other measurables. So it's perhaps not the best, but we hope that maybe in the future there's better measurements for this system. And basically now we can just run this, right? So I don't know, here it's chosen like dim, strong, dim, strong, and this can go on for a long time, right? And then we can fix these two parameters, which again, these are also empirically accessible. This is just the time that I leave the system connected to the light and flowing, and then the time that I just leave the system in the dark and letting it go to equilibrium by closing. So these are two parameters that I also have access experimentally. I'm going to set up actually a very simple, this is what I do, but really you can complicate it as much as you want, right? This is first, or if you want a marker chain, system that decides which environment is going to be chosen, right? It's like deciding a chain of environment states for the active phases, right? I'm using again, but please not be confused, green and yellow, but not to depict wavelength, rather to depict just intensity, which is what these systems are sensitive to. And you say, wait, but you could make something much more complicated, right? Much more correlated over time. And you can, that's absolutely true. But as I'm going to explain now, this is not going to affect the productivity patterns of the system. And I hope that I can explain why. So essentially, we already have our system set up, right? We have this thing that's going to be changing from completely closed. Now one is chosen as one, now it's chosen the other, now it's chosen this one, now it's chosen the other. We have some time parameters as well. And we just can like think of it, honestly, this is so different from, okay, I don't know what happened. But then we can see, unfortunately now you don't see the curve, right? But the curve is, that sucks, okay. Geez, okay. But the curve, you see it over here, right? You see it over here. These are the curves of, here I'm plotting relative concentration over there. relative to total concentration, including the solvent, or I'm sorry, the substrate. Honestly, this is not exactly what we were thinking about before, but I'm doing this because these curves, they do have them in the paper, and so these were the curves that we were trying to match with them, right? But in general, what I want you to look at is like, here I have, an environment that it's favoring the orange thing, and you see how it goes to saturation and it depletes the input of precursor, and now actually the other guy is actually going almost to extinction, okay? Now you choose another environment and things change. Interestingly, in between, when you let the system relax to equilibrium, they're kind of like, if you anthropomorphize them, they're kind of like figuring out a strategy for what's going to come next. And this is important because now we are contextualizing something that before was quite abstract, which is these preparation strategies, right? But now we can think of them a little bit more nuanced while thinking about these time-dependent sort of changes. Notice, for example, here we just come from a green state, right? And if you look at the concentration of the orange guy, the orange replicator, it comes from a down place. So, it reaches a value here, and then it hits, and it turns out to be favorable for him, right? So it just grows and reaches a steady state. But now, while relaxing, it doesn't relax to the same value. I don't know if you notice this point and this point are different, right? And this is imprinting in the system kind of a first order memory. This preparation state has a dependency only on the previous active state. And in a sense, what this means is that here's a bit formal, it's a bit weird to see it this way. Maybe I should have written that the side information that the system naturally, intrinsically displays is just what's the state of the environment right before, one step removed. That's the E minus. Maybe I should have written it words. That's the.
So what is happening in between the two colors? Like
you just let the system relax to equilibrium, and in fact, this is something that they do actually. Well, they don't do these experiments, but they show what happens, right? If you close the system and you turn off the lights, the system only reshuffles, and it's, of course, because it's closed, it tends to equilibrium. You just do that for a while. You don't even let it go all the way to equilibrium. Why do that? You can just stop this going to equilibrium at any point you want because you're the experimentalist.
And that time is always the same, like the relaxation.
That's a very good point, because if you move this time, right? If I now say, let's increase this time to relaxation, there's actually, before I wasn't letting it go all the way to equilibrium. But if now I do, right, I let it all the way to equilibrium, well, I'm always going to get to the same point here, right? Because this is the equilibrium value. Does it make sense? So under this limit, you don't have to go very far to have like sensible values here. You can say, these are all the same. I'm going to show you a plot where this applies now. And basically, you lost this side information. You see, now you no longer are correlated with the previous state of the active environment. And so Y here is no longer there, and you are under the other regime where I mentioned before that you have no side information. But this is accessible by this empirical parameter. I can move, this is the nice thing I think about this setup. By moving this empirical parameter, which is like, you set up the system, you establish a protocol, and you let it wait for this amount of time, the inactive amount of time. But I can just move this parameter as much as I want. And that actually gives me access to these two regimes. One in which I have side information about the just previous active state, right? Which is in terms of random variables, it gives me a one-step remove access to the marginal of P if you want. And then if you move this to infinity, you lose this information. And so you can study the two regimes by just having access to this parameter.
I'm not really sure if I agree with you in the previous setting that your state only depends on the previous state. I mean, if I have three oranges and three orange blocks in one row, I get a different initial condition than if I have green, orange. So
that's true. That's true. And this is only an approximation. But this is very true. Maybe you want to say something else, please. Finish.
That says that the total history depends on where you are.
Exactly.
Yeah.
Yes. Yes, indeed. And in fact, this becomes kind of like a fractal sort of object, right? Because if you want to solve for this, you need to account for all of the rest. That's exactly true, except that we are making an assumption here, which is like you're reaching steady state over here. That you're reaching steady state during activity. And if you don't have that, none of this applies. But if you reach steady state here, you also reach it here, you also reach it here. Literally, this reaching steady state kind of kills off the rest of. It's kind of like it's in this limit. This is the only contribution.
If you go to steady state, the influence of your initial condition is deleted.
Exactly from the previous history.
Yes. Okay.
Yes.
Yeah.
Remember, I made this assumption at the beginning, but it's actually something that we discussed whether it could be possible to generalize this to general trajectories. I think it would be a very interesting.
Yes. I would ask, could you get these two time scales directly from the mass equation of this process, or it's
Do I get them directly from the? Well, you can. Okay, you can. For example, what you can do, and actually, I did that. You can infer like what is the estimate for tau a, the time during activity, so that you can say with some percentage when are you for sure close to steady state, and that will kind of give you like an estimation of the error that you're gonna commit because you're not taking into account all the rest of the. I mean, in this estimation of the productivity, you're not taking into account all the rest of the history. I don't know if that's what you're asking.
yeah.
So yeah, you can estimate from the actual values of the parameters of the system what should be the tau a that you should input. And then tau e, as I was saying just before, is actually going to be one of my control variables. That's actually what I want to explore. Because, and I'm moving towards the end now, very quickly, because I think this is going over time. You can find, for this chemistry, you can find these are approximations, you can find what would be the closest to optimal strategy to maximize your productivity. And then these are simulations. So all the red dots here are simulations for different values of the strategy for which you are reshuffling during inactivity. I'm going a bit quickly, but I just want you to get the gist of it. So you're establishing this strategy, right? We can go to details later. You're establishing this strategy during the inactive phase. The inactive phase is basically run, remember, by the reshuffling transitions. So suppose that you have access to these rates, right? If you have access to these rates, you can just explore all of them, all right? And that's what we do with these red dots. We explore all of them. The black line here, especially this point here, is the prediction of what would be optimal if you impose the condition of bed hedging. I mean, it is not exactly, you see, it is not exactly the bound. These are the two bounds. Remember the curly P and curly P naught? These are the information theoretical bounds. We see how they are bounding effectively the system. We see that, in fact, they are quite close to saturation in many ways. And we also see that the little calculation that we made, which is an approximate calculation, kind of gives you the right answer for where are you going to find the maximal value of productivity. But what I'm moving here, by the way, is just the inactive time, right? And this also is nice because you observe that here you basically are above the upper bound of the no side information case, right? This is the upper bound for no side information, no variable y. But that's because intrinsically this system is observing this variable y by automatically intrinsically correlating itself with the immediate past. And this is the calculation when you assume that, okay? So it's quite good. And of course, when you move tau I to infinity, you break these correlations that are intrinsic to the system, this kind of like one-step removed memory that the system intrinsically has. And then you reach this bound, which is the one that you should have predicted at first, right? If you actually change, I mean, this is kind of very simple. If you change the units of this observable by using omega, which had to do with the number of replications per unit time, you actually make it so that you directly see that this protuberance here, right? It gives you indirect measure of the mutual information between, the winner replicator and the value of the random variable of the previous state of the environment. Right?
Was the different one also dependent on the gamma chart you had?
No, because it cancels in this limit. Yes, that's a very good point. Yeah. By the way, this is just like if you now say, no, I'm going to make a time series which is completely uncorrelated over time, right? Then, well, you are only bounded by the no side information. Of course, if there's like no information to be picked up from the system, you really don't pick any, and that's what you get. Okay, so it's the same curves, but now the way that we set these correlations of the environment is just like broken at priori, right? I don't know if that's the correct way of using that one. Great. I'm sorry to have gone over time. For me, this has been so awesome, but I don't know if you had comments all the way over here, but I'm just want to wrap up now. And so essentially, we've established this connection between information theoretic measurables, right, and productivity in reactor flows, thinking about autocatalytic reaction networks, very simple ones, extremely simple ones. And all of a sudden already we have seen that, oh, this is nice because we see that we can separate the different contributions as costs and benefits. And there's like in the one that we call it C anyway, we have this nice interpretation of an entropy term, a distance from optimal preparation, and also usage of site information, right? And we can see them at play as well in a kind of a minimal system that is based on, at least inspired by our actual replicator that exists in the lab. And it uses memory in this intrinsic way that I hope that I convince you that we can make it work, right? So for future work, it's funny because it has been already mentioned during this talk, which is amazing, which means that I hope that at least some things came across correctly. First off, you can think of higher order statistics because here we're just looking at the average. Right? And one question open is like, okay, if you look at other moments or other kinds of statistics, are there also information contributions that might be interesting or measurable? Indeed. And then another one is, of course, like, let's extend this to more proper framework of stochastic reaction, right? With master equations and so on. Well, with that, I would like to thank you for your attention. And I don't know how much time I went overboard. I apologize for that. I want to shout out, especially Artemi, with whom I collaborate closely on this project. These are other collaborators from Rochester University. And yes, so thank you for all the institutions that provide funding. And thank you for your attention.
Based on your next questions, how do you see this extended to more complex stochastic reactions? And how do you see this?
Well, what I think that's important here that's not being taken into account is outliers, right? Because these are just like ODEs. And I wonder whether, if you have, I mean, we know that these systems are not trivial. I mean, once you just like go from, these are nonlinear systems, but once you go from the simple ODE approach to actual stochastic master equations, there's this phenomenon, right, of bursts and all these kinds of events that they are essentially driven by noise, right? This is, I think, it could be boiled down to this concept of demographic noise that somebody mentioned before, right? And so that could actually maybe perhaps give us an interesting regime where, I don't know, maybe, hopefully, because we are interested in information, but hopefully you would have like maybe an important contribution that also is related to information theory, perhaps in the abundance of these like outlying or I don't know how to call this, like rare behaviors, right? And I don't know, this is pure speculation. I honestly haven't done the calculation, and I want to try to do this with two replicators, which is kind of like the minimal setup I would love to start with. But I have no profound insight to give you beyond that, I think. I don't know if you have an idea, maybe.
Feedback, because what you maybe thought would be also good to comments like this formally is that you can make a Fox-based representation on stochastic reactions.
The Doicolidi?
Yeah, Doicolidi.
Yeah.
And then you have a closed form for
Yes.
solution. But I always look that the solution has a statistical exist, but if you look to this closed form, I have an equation, then you can take it open.
Oh, you have it here already, it's done.
Yeah, no, it looks like a divergence thing.
A what? Huh?
Like a divergence in information theory.
Oh, wow.
So if you just extend, you just need to redo the Doicolidi and put the terms like information terms, not statistical physics terms.
Oh, yeah.
Like if you want to share it after the.
Yes, but what, so you say that somebody published something like that, or? Oh, you published something like this?
Yeah.
Oh, I would love to.
6 years ago, so I'm not excited, but
Awesome.
yeah, it's starting with the so.
Great. With self-replicators.
No, with enzyme kinetics, but
Oh, yes.
the formalism is similar.
I'd love to see that.
But it's like I want to say this is future work, okay, you need to go to the probability and then
Yes.
get each term, see which one is your divergence, which one is your cost, which one is your.
Exactly. Maybe we should talk about this
Yeah,
now.
I think Valve is doing much more than that.
Sure, I would really love to learn about this. I mean, at least I would like to read the paper.
Yeah, it is that,
But even before going to stochastics, you could just complicate the reaction networks.
Yeah.
And then I wonder whether this would be any useful at all, because you have to find different types of observables, you have to try to find what those observables are in terms of information theory, and
Exactly.
and it's not necessary that you can nicely split. It's not a priori expected that you can.
That you can find these contributions.
Yeah.
I 100% agree with you. And sometimes I worry that, replicators are, let's use the word, cooked,
Yes.
so that they come up with this, right?
Yes.
And it would be very interesting to try to figure out, like, if you could generalize these in a way that you can permit, I don't know, with some constraints, obviously, you're not gonna do very crazy, I don't know, third order reactions or something, but maybe with some sensible constraints, whether this is actually holding
Right.
for more general stoichiometric matrices or something.
Right.
Yes, I mean, this is obviously, I mean, it's not really a concern in the sense that, okay, this works, this is something to
Works
say.
with this
Yeah.
very idealized system.
But if we aim to generalize as much, I mean, let me also state something, but this is perhaps going into the kind of the philosophy of this, right? Like, we wanted this to be able to be at least ideally tested, right? And so we were very much driven by these findings of self-replicators and so on. So in a sense, we kind of like already knew what we were wanting to do. But I fully agree with you, and I also strive for generality as much as possible, or universality. So in this way, I think that, yeah, I suppose that that it would be interesting to look at. You can look at these flow equations in chemical reaction networks, see if you can do it from that with some, let's say, generic S-matrix, some generic stoichiometry. Yeah, that's a very good also direction. I mean, hopefully this is gonna inspire people to do also this kind of developments.
I was wondering if this last experiment where you apply switching oil or intensity switching, does this in some sense fit in the framework of piecewise deterministic Markov chains?
Piecewise deterministic Markov chains.
Yeah.
I don't know what, I'm sorry to say, but I don't know what you mean by that.
Okay, well, it's
You're a mathematician.
Yeah.
We lost it.
Yeah.
But I mean, the Markov chain is okay, but what the piecewise part?
Is that it's sort of switching between stochastic influences and then doing deterministic
All right.
flow, and then you do a stochastic jump, deterministic flow, stochastic jump, deterministic flow.
Exactly, because I mean, in a sense, it's just I think this is deterministic. Yeah,
Yeah.
it's super. That would be the craziest, simplest case, I suppose.
but
Yeah,
maybe this framework of, so of course, you can have maybe we should.
because there's a formalism that's
Yeah, it's all formula for this. I'm not sure if it correctly applies here, but
piecewise Markov chain.
piecewise deterministic Markov chains,
Okay.
if I remember the name correctly, but yeah.
I mean,
But
to be
if you haven't heard about it, you don't need to speculate now about.
no. No, of course, I didn't like come from piecewise deterministic Markov chains and say, I'm going to use that for this. No, I was thinking literally kind of like more of like, I don't know, I want to say like a physical perspective, say, okay, how do I do that? How do I actually implement this? Okay, so I can make the system go to equilibrium and let that be my way of establishing a strategy, right? Quote unquote, because I'm always using this analogy with Kelly. And then let's actually move back to the gambling phase. It really was very much based on the question of how do you bring from Kelly to the chemical reactions, right? But in a way that it makes sense. And you can have like 1,000 or 1,000,000 reactors, and then you send them in with some distribution, something that you can do with one reactor over time. And I mean, out of that, it was nice because we had these. You had to think about, oh my God, but then there's these correlations over time, and you can use them as side information, which was kind of fun. And unexpected at the point. Yeah. But so my point being is that, of course, I've never heard of this before. I'm sorry, I should have.
No.
But maybe there's some interesting result there that could be applied here, and perhaps these derivations are more direct from there. I don't know. Yeah. Okay.
Time for lunch.
Well, thank you, guys.